Okay, so we're looking at different properties of liquids, and we know from the past that liquids have low compressibility, lack of rigidity, and high density. So some of the properties of liquids we have are the surface tension. So what surface tension again is resistance of a liquid to increase its surface area. So if our liquid has large intermolecular forces, then what's going to happen is they're going to have a high surface tension. Okay, so they are going to want to resist that increase in its surface area because it has that high surface tension or large intermolecular forces, strong intermolecular forces holding it together. Capillary action, you should know from biology, capillary action is that spontaneous rising up a narrow tube of a liquid. So there are two things going on in capillary action. You have cohesive forces, which is among the molecules. So those molecules interacting with each other in the liquid. And then you have the adhesive, and that is the liquid molecules and the container. Those forces between the container and the liquid. And then we have viscosity, which is the liquid's resistance to flow. So if you think of liquids with large intermolecular forces, they're going to be highly viscous as opposed to those with low intermolecular forces.
Is that viscosity
Like lava, molasses has low or is highly viscous. And it's a big sugar molecule, so it has lots of LDF in there. Okay, so the next thing I want to look at is why do we form the meniscus in a narrow tube? So there are two different types of meniscus. You need to know the convex and the concave. So the convex, what we're going to see here, we have a convex, and what's happening within the convex is these cohesive forces between the molecules itself of that liquid mercury are really brought together, bring each other together, and they don't want to interact. They rather interact with another molecule that's same rather than the molecule of whatever it's in. And then you have the concave, okay? And the concave, what's happening here is we have this high interaction between the molecules of the liquid and the molecules of the tube. So we have adhesive forces that are working at play in there. Yes?
with the adhesive forces, we measure bottom of meniscus. What about convex? Convex meniscus, can we measure the top or bottom?
I would say it would be that bottom, because they're mostly it's going up higher because they have those forces amongst themselves. Okay. All right. So then we have the types of solids, and you looked at this yesterday in your POGL. We have ionic crystalline solids, which have high melting and boiling points, soluble in water, conduct electricity, and aqueous and molten states. And so ionic crystalline solids are going to be composed of metal, non-metal, metal, polyatomic ion, or a polyatomic ion and a polyatomic ion. I think the metalloid's going to come in more with the network. We're going to talk about those. So then we have your covalent solids. These are going to be your molecules. You should remember back from regular chemistry, you have low melting points and boiling points. Generally, they are not soluble in water, and they do not conduct electricity in any state. So they do not conduct electricity because we have no ions in there. So the new one that we learned was network covalent solids. So what these are, they have high melting points and boiling points, not soluble in water, do not conduct electricity in any state. So the ones that the AP is really concerned about that you know are going to be any of those carbon molecules that have that 3D bonding upon itself. So diamond, graphene, all those carbons strongly bonding to another carbon. And then anything with silicon in it, so silicon dioxide, anything with that silicon in it is going to be a network covalent bond. Or solid, sorry. And then you have your metallic. And these have high melting points, high boiling points, not soluble in water, conduct electricity in solid and molten states. And why are they able to conduct electricity? The what? The electron C. Okay, so electron C is great, but that would be a lower chemistry term. So we are going to be in AP chemistry, we're going to say, because of the delocalized electrons. And then sometimes you're going to have lone atom solids. And these are nonmetals. And what do I mean by what type would I mean is probably sulfur or phosphorus, those types of atoms. And when we look at those, the sulfur or the phosphorus, you're going to have LDF forces at play in there. Yes?
Why would they bind to each other? It's just one of it, like a vacuum, or
Sorry, what was that?
is it like one just in a vacuum? Or is it a group of them? Because if you're a group of them, why won't the bind to them? Are they just being moved around too much?
So what sulfur does, sulfur naturally occurs as an S8. Or in P naturally occurs as a P4. So they're kind of like covalently, but it's a lone atom. I don't know. That's weird.
So they're disconnected from each other.
Mm-hmm.
And they get stuck on each other, shaking on each other,
Mm-hmm.
kind of like fat.
So here are some pictures. You have carbon. So you have this 3D network of this carbon that gives us that network covalent solid. And then you have your salts here, your sodium chloride. So here you have your sodium and your chloride and your chlorine and your sodium. And they make that lattice and give us that solid. And then here you have ice, and you have these intermolecular forces holding these molecules together and creating that solid. So if you will look here, this is diamond and graphite. So those are your carbon network covalent solids. And if you see between graphite, so what's in your pencil, you have this nice layer of carbons, and then it's connected to another layer, and then connected through another layer, and they're connected through these London dispersion forces. And these forces are weak. And so when you're writing with your pencil, what's actually happening is when you touch that paper, the London dispersion, and you start putting pressure, London dispersion breaks, and you start getting these little pieces of the graphite writing on, transferring to your paper. Huh?
How do they get on the paper like that?
And then here's another network covalent solid talking about the p orbitals and the pi system in graphite. All right, so ceramics, very hard. Ceramics are network covalent solids because they contain silicates. And then you have semiconductors, just a little exposure to semiconductors, not really going to lecture on that. So again, here you have your metals and you have your sea of mobile valence electrons, or what we're going to say is delocalized electrons. And that gives us all those beautiful properties of metals. Questions? All right. So, solutions, we usually talk about solutions, we think of liquids, but this alloys are, metal alloys are also solutions, though they're just solid. So you need to know the two types of alloys. They're a substitutional alloy, which is where they take out the host metal, some of the host metal atoms, and they replace it with another metal of a similar size. So we're just substituting in another atom of a similar size. And it says that brass is a substitutional alloy. So you have copper and zinc, and they're about the same size. Whereas you have an interstitial alloy, and this is where you have this metal structure, and what they do is they will pack in some smaller atoms in there. Here we have carbon being packed into iron. Okay, so we put it in those little empty spaces, and that gives us steel. So you need to know the difference and be able to draw a substitutional and an interstitial alloy. Questions? All right, let's fill out this chart. So, give me an example. We have covalent network, metallic, lone atoms, and those are all going to be our atomic structures, and then we have a molecular structure and ionic structure. So, an atomic covalent network example. Silicon dioxide. So, what are our big ones in AP? We care about silicon dioxide and any of our carbons. Solid carbon. Metallic. So give me some metallic atoms. Iron. What else? Gold. Silver. Okay. And any lone atoms, those two special lone atoms. Sulfur and phosphorus. Give me a solid non-metal molecule. What'd you say? CH4, if we brought the temperature down low enough and made it into a solid, because usually it's a gas, but CH4 as a solid. Ice. Or maybe glucose. And then give me some salts. NaCl. Potassium chloride. KCl. K through PO4. Good. Okay, so those are some examples. So what type of bonding is going to occur in our covalent network? If you think of carbon, what type of bonding do we have there? It's a 3D or a 2D covalent bonding, which gives us a strong lattice. What about metallic? What type of bonding do we have in metallic? Metallic. Which gives us what so special in there? Delocalize electrons. Lone atoms, what kind of forces do we have in those? LDF. Non-metal solids, what is holding them together? Dipole and LDF. And these, what is holding each molecule together within is covalent bond. And then an ionic type of bonding do we have there, or what type of structure? Crystal lattice. And we have ions being held together by electrostatic interaction. And lastly, we're going to go with the property. So give me a property of a covalent network. So a diamond, what do we know about a diamond? High melting point. No electricity. Huh? Not soluble. And the big thing is these are very, very strong. What about your metallic? Conduct electricity. Did you say not soluble? Malleable? Ductile? High melting point? What about lone atoms? So these guys have low melting points and they're highly volatile. Our nonmetals is going to vary depending on our intermolecular force. And our ionic salts, these guys are brittle. Most of them are soluble. And they have high melting points. Questions? Okay, so this is just rehashing those kind of what we just went over. So you can go back and look at that. But now what I want to do is fill this out, and we want to say, is it atomic, which means lone atom, molecular, metallic, network, covalent, or ionic? So I want to put network above covalent. Network, covalent. So O2, how would you classify that? Lone atom. H2S. Molecular. Silver. Metallic. Potassium chloride. Ionic. Silicon silicon. Covalent. Network. Aluminum sulfate. Ionic. Neon. Lone atom. Silicon dioxide. Network covalent. Ammonia. Molecular. Magnesium magnesium oxide. Ionic. Sodium hydroxide. Ionic. Methane. Molecular. So looking at this chart here, these different properties, tell me what type of molecule is A? What type of solid is A? Metallic. What about B? Covalent. C. Ionic. D. Network covalent. Any questions on those?
So, molecular and network covalent, the difference is, like, what's the difference?
Network covalent has that really strong interaction between those molecules. You see how that has that really high melting point and boiling point?
Yeah,
But MB, it doesn't have a really high melting point. It's
that's why.
And B has a low melting point, low boiling point.
So it's just, is that like?
So that would be covalent. So any covalent compound, sugar.
Okay, but like in the first part of what we did, I guess. Like what makes H2S?
Okay, so anything that's going to be network covalent that we really care about is going to be those anything that's carbon solid or your silicon containing.
So just silicon. I just was wondering how silicon, like on its own, was covalent. Because of silicon.
Just because it's yeah. Like anything, if it had carbon on there, and it would just been carbon diamond, or if it said carbon graphene, or graphite, those would all be network covalent. What makes them molecular? Non-metal?
So like when we said B in the second part was covalent, in the first part that would have been just molecular.
Oh, yeah, I see what you're saying. Covalent bond, which is molecular, yes.
Yeah.
Sorry. Okay, so vapor pressure is the pressure due to particles of a substance in vapor phase above it's liquid. So if I have this liquid here in this container, closed container, these particles that are in here, okay, some of them are going to get enough kinetic energy and they're going to come out of solution. Okay, and they're going to go into the gas phase. And when they do that, they're going to exert some pressure upon the liquid that's below it. Okay? So if I look at these molecules that I have up here in this graph, I have diethyl ether, which would look like this, C2H05, have an O, and then all the other side is C2H5. So looking at that formula, what type of molecule do you think it's going to be? Polar, nonpolar? Nonpolar, which means it's going to have what forces holding it together? What intermolecular force? LDF. We have an alcohol over here, ethanol. Anything with an OH on it is going to be a polar molecule. And this is going to be a hydrogen bond because we have O and H in there. And then water, we know, is polar, and we know that water is hydrogen bonds. So if we look here, who has a lower vapor pressure? Which one is easier to become vapor, come out of liquid solution and become vapor? Okay, so our diethyl ether, right? So the diethyl ether easily becomes vapor. And what type of, how strong is its intermolecular force compared to those other ones? Pretty weak. So if you were to be given this question and said, why, tell me why is LDF, or why is diethyl ether have a lower vapor pressure than the other two liquids, then what you would say is that the stronger the intermolecular force, then the lower the vapor pressure. Okay?
So does that mean that by looking at it, you can also tell like the boiling point? And like tell which one has a higher and lower boiling point?
Yes.
And then I have one more question. What constitutes it as boiling if there's always vapors being given off? Other second boiling points.
So boiling point is going to be when your atmospheric pressure is equal to your vapor pressure. Okay, and I have a slide that comes up about that here in a minute. So we have two polar molecules left behind, and why is ethanol have a lower vapor pressure than, or a higher vapor pressure than water? They're both polar.
Because water has more hydrogen.
Yes, because water has more hydrogen bonds. Therefore, it has a lower vapor pressure. Okay? Now, if we are looking at a closed container, everybody good with the slide before I move on? So if we look at a closed system, when we initially close the system, what is going on is that we have water going from a liquid phase to the gas phase. As time goes by, at equilibrium, then what we see is the amount of water going from liquid is in equilibrium with the amount of water going into the gas phase. So you see you have some coming out, and as you have some coming out, you have some that get enough kinetic energy and go into solution. Okay, so and that's at equilibrium. So let's look at vapor pressure at equilibrium. So what happens here is we have no more net change in the amount going into liquid or into gas. Balance each other out. So I want to know, what's the vapor pressure of water at 100 degrees Celsius? So we know at 100 degrees Celsius what happens to water. What is this equal to? The boiling point. So that's equal to our boiling point. That's where we have liquid becoming our gas. So the definition that I just gave Marcus, the boiling point, the definition of boiling point is when your atmospheric pressure is equal to your vapor pressure. So, yes, so if we were to say, if we were at normal atmosphere, or at normal pressure, which would be standard, which would be 1 atmosphere, then that would be when our vapor pressure is equal to our boiling point. So we would say that that would be at 1 atmosphere, or normal pressure. We're assuming that this is at sea level or not up in the mountains or anything, okay? And then so therefore our vapor pressure would be 1 atmosphere, or whatever's normal wherever we're at. Questions? So let's take a look at vapor pressure real quick. Here is a old school barometer. What we have here is you have, say, mercury in this dish, and you have this tube, and you have atmospheric pressure, or pressure, that is pushing down on that liquid. And what you have here is the, so this is in a vacuum. So when the atmosphere presses down on that, then what we see is we see the liquid rise up so much. And they say, and that is 760 torr, but if this is mercury, then it would be 760 millimeters of mercury. Now, if we were to take that same thing and put it over some water, what we're going to see is we're going to have our vapor pressure, or our atmospheric pressure, but we also have vapor pressure from our water that is counteracting that, pushing up against it. So we see that the column moves down a little bit. Instead of being at 760, now it's down at 736. So you take that difference, and when you take that difference, that gives you the vapor pressure of water, which is 24 torr. Now we take it, we have ethanol, so we put this over ethanol, and what we see here is we still have the atmosphere pressing down on here, but then we also have our ethanol vapor pressure, and it's pushing it down a little bit further, and what we get is that difference to give us the vapor pressure of ethanol, which is 65. And then you see diethyl ether. Here you have, again, you still have your atmospheric pressure, but this diethyl ether is really pushing back down on that mercury. And when we have that, we see that vapor pressure, that difference is 545 torr. So very high vapor pressure. Okay? So be prepared to look at different things such as a graph like here. And this is what we just looked at. And just be able to answer questions from that graph about what's going on. And lastly, we have Clausius-Clapeyron. It's an equation. And you don't have to memorize this, but what Clausius-Clapeyron does is we take into account vapor pressures, and we are able to find the enthalpy of vaporization. What's another word for vaporization? Boiling point. Okay, and so just remember you have R, we're going to use the energy, R, and temperature has to be in Kelvin. So you have several homeworks that you could probably be doing, B and C, I think. I've lectured through enough so you can get through B and C. And then tomorrow I will hopefully finish this up. Ooh, there's still a lot there. No, oh no.
Change in H is boiling?
Yes. So that's going to be how much energy you need to get to boiling point.